Okay, so I was quite excited in the first half of section 3.9, and that's because I am. How can you not be excited about something like that? We have just discovered a function whose derivative is itself, and we have found another function whose derivative is the reciprocal function 1 over x, right? So that's really cool. All right, now let's use a different base for that. Okay, so b is any base, and for mathematical reasons, okay, you want b to be a positive number because the base, negative base, is not going to make sense for logarithmic functions. And also, we don't want b to be equal to 1 because, you know, if b is equal to 1, 1 to raise to anything is always going to be 1. And so that's kind of boring. And this whole theory is not going to work if b is 1 or 0 or negative. Right, so we assume that b is the space that is not 1 and positive. With that assumption, we are trying to find the derivative of this, okay? But we don't really have any nice way of doing this, right? Or do we? Yeah, the idea is to use, again, implicit differentiation. Let's see what we can do. Can you rewrite this as an exponential expression? Sure. If you say y is log base b of x, what we are saying is b to the y, y is the exponent. The value of the log function is always the exponent. B to the y is equal to x, okay? That is the definition of the statement, y is equal to log base b of x. And now you take log of both sides and differentiate. What do we call this? Yes, logarithmic differentiation, right? So you have log of by is equal to, when I say log, I mean the natural log. And by the way, that is the consensus in the scientific, engineering, and mathematical world. When you say the logarithm, we just assume that we use the most natural base, which is e. Right? So when I say the log, I mean ln, which is the natural logarithm. All right, now y can be moved into the front, right? Which is one of the nicest things about any kind of logarithms. And so you have this. Now remember, this is a constant. So y, oh, yeah, okay. So we haven't really done anything yet. We have to take the derivative at some point. And in fact, we have to erase this first. All right, so it's log b, that's just the number, okay? Times the derivative of y, because y simply becomes y prime when you take the derivative of this left-hand side. Remember, this is constant, so this just stays. I mean, this is like 5 or 20 or something. And then this side, of course, becomes, I should write down what I am doing. Now differentiate, and you get this, okay? So that means y prime is 1 over x times 1 over the natural log of b. It's sort of unsatisfying, huh? It's not as pretty as before. Notice here, if b happens to be e, then this whole thing becomes 1. So you just get 1 over x as we saw before, right? So in a sense, this little extra thing is here only because we decided to use rebelliously the number b instead of e. Okay, if you used e, almost it's like the universe, mathematical universe saying you should have used e, but you know you wanted to use some other number b, so I'm going to let you use it, but the world will not be that pretty. Look how ugly this derivative is. You just have to have that adjuster, you know, something that modifies the beautiful expression 1 over x. So you have to have this in addition if you decide to use any other unnatural base like b. And so this is like the penalty for using something other than e. Okay, and that's why I have been saying e is the most natural number that should be used for the base of a logarithm. And so when they use e as the base of a logarithm, they call that the natural logarithm. All right, so that's that. All right, next, we let y is equal to b of x. y is equal to b of x. Okay. Let's take the log of both sides again. Why do we do that? Okay. Because that's going to allow us to find the derivative of b to the x. All right, so that would be, what is that? It's a log of b to the x, which you can write as x times log of b. Again, this is a constant, okay? It's like number 7 or something like that. Take the, now differentiate both sides. And you get 1 over y, that's it. No, times y prime. Remember implicit differentiation. Y is considered a function y of x. So when you differentiate this, you get 1 over y times the derivative of the function y, which is y prime. This side, remember, this is constant, like 7. If you have 7x, the derivative of that is 7. So the derivative of the right-hand side is just the natural log of b, a constant. Okay, so now we can easily come up with the answer. Y prime is y times the natural log of b. Remember, if b was the natural choice e, then this part will just be 1, and y prime would simply be y, as we saw before, right? If y is e to the x, then y prime is also e to the x. So once again, this extra additional constant, a scalar, has to be there to adjust for not using the most natural base e. If you insist on using b, you have to pay the price, the penalty, which is this ugly thing you have to attach at the end of y when you take the derivative of that exponential function. All right. Once again, you see e must be the most natural choice to be used for the base of the exponential function as well as the derivative function. Okay. So I actually did not. I have been using this thing called logarithmic differentiation, because that's what I have been using. You take the log of both sides first, and then you differentiate both sides using implicit differentiation. I probably should have mentioned that expression, the logarithmic differentiation, earlier. But now that we have seen this twice, I will formally introduce you to the idea of logarithmic differentiation. Actually, we should, before that, I should just do a couple of examples. All right, if y is 3 to the x, what's y prime? Well, I mean, we just did this. This will be 3 to the x times the natural log of 3. So that natural log of 3 is the adjuster, or the adjustment factor that you have to use. Okay, the common log of x, which is the implicit base 10 of x. Now, this is again used often in things like engineering, like when astronomers study the brightness of stars, or acoustics in the sound loudness intensity, or the earthquake intensity. They all use the scale that is based on base 10 logs. Okay, so this is something that's used, but it is an unnatural choice for in terms of calculus. All right, so this is the derivative. This is the function. Then the derivative is going to be 1 over x times, remember, log. Oops, it's right here. The natural log of the new base comes in the denominator, so it's going to be a log of 10. Okay, so that is the derivative. All right, so logarithmic differentiation. This is the very last thing we are going to do in chapter 3. All right, so logarithmic differentiation, sorry, I can't write and speak at the same time. Logarithmic differentiation. What in the world is this? So once you are given the function, okay, you take the log of both sides. All right, and so one side will become, the natural log of y. Okay, and then you take the derivative of both sides, and so this is a type of implicit differentiation. And then you eventually solve for y prime, so that you can describe or you can explain what the derivative is. And this is used whenever you have an exponent which involves x. That is the typical use of this logarithmic differentiation. Let me illustrate what I'm talking about. This is really the only thing I have to explain. And the rest is just using examples or illustrative exercises to show you how to do this. All right, so let's say you have this function, which is x cubed plus 1 raised to the 2x. You are not going to see too many functions like this where you have x as a part of your base and exponent, but sometimes you do. Okay, well, unfortunately, sometimes you do, and that's fine. Okay, now if you try to take the derivative of this using anything else, you can't. It's going to be really, well, I don't know if you can. It's going to be very, very hard. All right. So what you can do is to practice this or to implement this thing called logarithmic differentiation. You take the log of both sides. Ln of y is ln of the right-hand side. But remember, the natural log allows, or any kind of log allows you to write the exponent as a coefficient in front. Okay, so now you have the product of two functions on the right-hand side. And then you take the derivative that differentiate both sides. You get 1 over y times y prime. This is implicit differentiation. This side, you will have to use the product rule, right? The derivative of the first times the second plus the first times the derivative of the second, which is x cubed plus 1 under the derivative of the inside function, which is 3x squared. Okay, so this is a long expression, 2 log of x cubed plus 1 plus, let's just combine these. It's 6x cubed all over x cubed plus 1. I'm not done yet. Okay, now you just have to multiply both sides by y. But y is this thing, right? So now you multiply by y, and it's even going to be even uglier. When I multiply both sides by y, let's just write this down. It's x cubed plus 1 to the 2x power. And then you write everything else that used to be on the right-hand side. That, okay? As ugly as it is, we actually did find the answer to the question, what is the derivative of this horrendous looking function, right? And there is the answer. It looks even more terrifying, but we were able to do that. So that's the power of logarithmic differentiation. All right, we are going to do one more thing. Let's say 2 more examples, right? What happens when you have x to the x power? Okay, this is probably easier than last one, right? Okay, you take the log of both sides, which is x times log of x. Notice here, many times you have to use the product rule on one side. Now you differentiate this. The left-hand side is 1 over y times y prime. The other side, this side becomes the derivative of the first times the second plus first times the derivative of the second, okay? And so this is just a log of x plus 1, okay? Now y prime is x to the x. You remember you multiply both sides by y, which is x to the x. And then you just add or rewrite the right-hand side. So that, actually, I don't feel comfortable. Can I just go ahead and write 1 in front? Okay. And the reason I do this is because this one is a little ambiguous. I know we don't mean it's not log of x plus 1, but it sort of looks like it. So in order to avoid the ambiguity, I feel much more comfortable rewriting this as 1 plus the ln of x. Okay. All right. Y, this is the last thing I'm going to say, promise. All right. Let's say R is any real number. Now we know what the answer is if it's a rational number, because we had that even more, whatever, the more extended power rule, right? And the answer was r times x to the r minus 1. We knew that for rational numbers. Now, what happens if it's any real number, like irrational number, like pi, or e, or pi squared or something? Well, we'll find out. What is that? Okay, you take the log of both sides, and that's going to be log of xr, which is r times log of x. Differentiating left-hand side will yield 1 over y times y prime. R is a constant, so this will just become r over x. There's no complicated power rule or product rule necessary, because r is simply a constant. So r times the derivative of natural log of x, which is 1 over x. So y prime is going to be y times r over x, right? And of course, that's xr times that. So what is that? It's r times x to the power of r divided by x. That's r minus 1. Remember, you subtract x. Basically what you have is x to the r divided by x to the first. And the new exponent will be r minus 1. So this is what you get. And of course, it's not surprising anymore, because calculus is so systematic, and everything seems to be so consistent. The way you get that is to move this r to the front and subtract 1 from the original exponent to get the new exponent. That now is true for any real number. So the very, very last thing we write here at the end of chapter 3 on how to differentiate all kinds of functions is this: for any not positive integer only, not positive and negative integers only, not even for rational numbers only, but now, for the first time, for any real number r, the derivative of x to the r happens to be r times x to the r minus 1. You move the exponent to the front as the coefficient, and the new exponent is 1 less than the original exponent. All right, so when you have, and you probably would not have to work with this, but if you have x to the pi, then the derivative will be pi times x to the pi minus 1. You will probably never use this really, but theoretically, this is quite possible. And so now we have the final version of this, and this is called the power rule in its full glory, the full version of the power rule. And that is a beautiful end to a chapter. So thank you for your attention. We have just completed chapter 3, and now we are going to chapter 4, where we are going to use and learn how to apply this wonderful knowledge, which has to do with differentiation and derivatives. Okay, congratulations on finishing and completing chapter 3. Go celebrate.